Just to make sure everyone sees my slides, right? And hears me well, I hope. If there is any issue, please let me know. So it's my great honor to be part of this lecture series, the SIGBED Distinguished Lecture Series, which is an amazing opportunity for me to talk about some of the things that I think are relevant for research, but also great opportunity to interact and hear your comments and questions and eventually provide new ideas for improving the state of the art in the field. So what I'm going to talk about today is mostly what I did in the last 3-4 years, but as you will see during my presentation, this connects deeply with previous research that I carried over 3 important decades where we've seen 3 paradigm shifts, namely the low power paradigm shift, mostly early 90s when it started, and the focus was to make computation more efficient from a power consumption perspective. Then the cyber physical system wave, which started in early 2000s. And in that case, the sensing and the computation with multi-core designs was brought together, and the focus in this case was mostly on communication to make it efficient in addition to the computation. And finally is the third wave after 2010, which is the wave of AI, ML type of systems. And the emphasis is on knowledge, efficient knowledge processing, such that we can design the systems that we envision only today. So if you ask me what's the grand vision, what's my grand vision about learning with in this 21st century, I think the one of the central problems is learning with limited resources. And in this talk, I'm going to emphasize on two things. First, the role of abstractions, meaning models, which are critical for optimization of these intelligent systems. And second is the constant strive for efficiency in system design, in particular power efficiency, which drives the proliferation of mobile devices, IoT devices, and in general, energy efficient computing. So it's interesting to note that this efficiency concern permeates all these 3 decades that I mentioned. And the emphasis changed dramatically from efficient computation to the power efficiency, which still dominates a lot of research these days. And particularly if you think about the sustainability of these systems, this will remain one of the main drivers. So in my talk, I'll highlight a few research problems that played a major part in my experience in AI and ML system design, particularly for these mobile applications. And my hope is that if I'm not going to make you learn much, at least I hope I inspire you to contribute to this important area of research, because there are exciting times ahead of us. So previous keynotes addressed fundamental questions on, say, trustworthiness or timing issues in cyber-physical systems, which are, of course, paramount to this area. Today, I'm going to talk about something slightly different, namely about things, networks, and AI, as well as their subtle relationship that, once understood, can let us run deep learning models with limited resources. This is precisely what makes the distributed learning area such an exciting area of research. So just to anchor a little bit my talk, think of this 3-layer abstraction that I'm showing here, where at the top level we have the clouds, which are typically infinite or quasi-infinite resources. Then we have the middle layer, which is dominated by the edge nodes, and this is more limited in terms of compute power, is prone to errors or downtimes, but the big advantage is that it offers low latency due to the physical proximity to the users. And at the bottom layer here, we have the myriad of devices like IoT devices, cell phones, robots, self-driving cars, whatever, which are much less powerful in terms of computational resources and even storage capacities, but usually run on batteries. So therefore, when designing this kind of systems, it's critical to account for this kind of limitations. So in my talk today, I'm going to follow two main ideas, meaning the efficient design of deep neural networks is one of them. And second, try to illustrate how one can account for resource limitations, which could be hardware, for instance, could be memory, could be latency, but also power consumption, which comes into the picture as an important constraint. So let me start with a simple question. If I show you the network at the top, in the top half of this image, would you know how to design this network? This was, by the way, the GoogleNet proposal 10 years ago, a very famous network to date. And probably the answer is most likely no. And in general, there are very few experts or even companies that can afford this type of ad hoc design that provides outstanding results. So even a better example, imagine that you have a brand new data set and you're trying to find a neural network that achieves the high validation accuracy on this data set. So you choose a particular implementation, and after many hours of training, you realize that the accuracy is, say, 80%. After more tweaking, you realize that, and maybe a lot more GPU hours, you realize that, well, you made this accuracy close to 85%. So the question is, are there even better neural networks out there that can improve on this? And obviously, another question is, how can we make this process faster? So this is essentially what suggests this, one of the core ideas that I'm going to cover in this talk, which is the idea of neural architecture search, which leads me to the second example shown in the lower half of this screen, which is another famous network proposed some years later, namely EfficientNet B0. So the difference between the first and the second is that the second was discovered using NAS, using neural architecture search. So while the first one was a super interesting exercise in creativity, people from Google with a lot of experience, a lot of intuition, a lot of good sense of how things are working, the second one is a systematic process behind it, and this is the neural architecture search. And this, once this base B0 was created, then by using appropriate scaling, it has been scaled up in terms of depth, width, and even resolution. So a family of networks emerged from this about efficient B0, EfficientNet B0 being the last one and the most performant one. So the interesting thing is that not only this comes through a systematic design, but it's interesting to notice that the EfficientNet actually achieves better accuracy than GoogleNet with fewer parameters and fewer number of flops. So the question is then, what's the secret behind designing efficient neural networks? What are the right abstractions and models that we can use to derive such systematic solutions? So to address this thing, these questions in this talk, I'm going to structure this talk in two parts. In the first one, I'm going to discuss the issue of optimizing AI for resource-constrained environments. So more specifically, I'm going to introduce the basis of neural architecture search and some zero-shot proxies and their theoretical underpinnings. We'll then discuss something about the efficient training of adaptive neural networks to better use the available resources. In part two, I'm going to look at the broader implications of these ideas. And specifically, I'm going to suggest two interesting applications. One is distributed on-device depth estimation, and the second one is what I call batteryless AI. So my talk is basically an exercise in efficiency for AI and ML systems design. First, focusing on ways to discover new architectures, hopefully optimal architectures, and then the focus shifts to efficiently training such architectures once discovered. So let me start by setting the basics for this neural architecture search, or NAS for short. So from a high-level perspective, NAS can be regarded as an optimization problem with specific targets. So for instance, high accuracy or a few parameters or things of that nature. It's sort of similar to design automation for ASIC and processors many decades ago. So NAS obviously has attracted significant attention from both industry and academia. And to give an intuition what's behind it, so we start with a set of candidate architectures that define the search space. This could be either template-based or cell-based. And then we have an optimizer which defines the search, the search algorithm. And here we have multiple classes. So we have so-called multi-shot methods, which have typically rely on reinforcement learning. We have one-shot methods. Typical example is differential architecture search. And both of them have many interesting success stories, but they have a couple of problems that are very important. One of them is that they are mostly trial and error in nature, involving network training in the optimization loop. So this leads to a very time-consuming process and intensive computational resources requirements. The second issue is that they don't necessarily consider the hardware constraints like latency or energy, for instance. And more importantly, they do not address the fundamental question of why certain architectures by NAS perform better than some sort of hand-designed architectures for some target task. So in the last few years, a new wave in the research in this problem space brought us so-called zero-shot methods, okay, which are essentially relying on some proxies or metrics to indicate the test performance of a given architecture without this excessive and time-consuming training. So we note that even the simplest metrics, like number of parameters that characterizes a design or number of flops, can be seen ultimately as this kind of zero-shot proxies, simply because they don't involve training, okay? So obviously there are a wide range of proxies that have been proposed, and they have more or less success depending on the type of designs that we're talking about, and particularly when accounting for constraints like hardware constraints that need to be satisfied for certain designs. So just to give a sense of what's going on here, multi-shot NAS approaches first generate the controller for this approach generates first a network description from the search space. Then we translate this network description into a real neural network, and then we train this one until we get the performance number that we want. So this is an iterative process and involves explicit training at every step. So it can take a lot of time, sometimes thousands of GPU hours, so is not very efficient. Representative examples are, for instance, NASNet from Google Brain, which was one of the early designs, and more recently, the efficient net that I was mentioning, which is also relying on reinforcement learning. And the bottom line is that this approach is, although not very efficient, illustrated the power of NAS to generate systematically this kind of architectures that are eventually used in resource-constrained environments. A more efficient type of approach is the class of one-shot approaches, which only trains a single layer that contains all the candidate networks as the entire across the entire search space. In this representation, each node is a feature map, as shown here, and each edge here denotes a certain type of operation. So we first create a network combining all these candidates, then we train this hyper network to identify the importance of these operations. And for instance, here In this slide, the more important operations are shown with thicker lines. And finally, the output architecture is produced by selecting the most important operations on each edge. And this brought significant improvement in the range of tens or maybe 100 GPU hours, and even newer versions that involve weight sharing methods cut down the time even more to a few GPU hours in some cases. So the bottom line is that training is still required in this type of approaches. You may wonder how these approaches fare when we compare them. So say we have an application space that ranges from image classification all the way to speech recognition. We have a bunch of architectures that are used to implement them. Could be a server, could be a mobile phone, could be some microcontroller. And in this representation, I show something a little bit perhaps less usual, which is on the y-axis, we have the top accuracy on ImageNet. On the x-axis, we have the search cost in CO2 emissions. And just looking at these bubbles here, where the diameter shows is proportional to the number of multiply accumulate operations, we can see that the zero-shot approaches are actually quite more efficient compared to the multi-shot or the single-shot approaches at a fraction of the cost in terms of CO2 emissions. So they perform quite well, quite high accuracy, as you see in this case here, but in terms of emissions, they are very low. And also here is another set of points that are not extremely powerful in terms of accuracy results, but still very low signature footprint when it comes to CO2 emissions. So these are concerns that these days are gaining some momentum because of the sustainability issue that I was mentioning. Some of these data centers, I've seen recently some plots showing that need more electricity than some of the countries around the world. So this is a significant concern if you want to produce these things very efficiently. So let's delve now a little bit more into these zero-shot approaches and specifically talk a little bit about the proxies. In general, ideally, accuracy proxy should address three primary concerns. Should be expressive, meaning should have the ability to model complex patterns. Then it should have a good generalization capability. In other words, the proxy should also reflect the network ability to generalize from training data to unseen out of the distribution data. And finally, should be very trainable. In other words, the proxy should indicate how we can quickly converge to a desirable performance model. And from this perspective, we could summarize that what a good proxy does for deep network design is provide insights into the network capacity to learn complex representations, to generalize to unseen data, and then to converge to a minimal loss values. So in this talk, I'm going to cover two classes of proxies that have been proposed so far, meaning gradient-based and gradient-free accuracy proxies, just to give you a sense of how this can work in practical examples. There are many, let's start with the gradient-based proxies. There are many proposals that have been put forth in the last few years. I'm going to talk about two of them just for the sake of giving you a sense of what's going on. So the first one is so-called SNP, single-shot network pruning. So it's a technique that was initially designed for pruning neural networks, but has been adapted for neural architecture search. So when the key ideas behind SNP are to determine the importance of the weights of the network parameters and basically prune those that are less important and focus on the ones that are important that are considered during the training process. So as you can see here, we define a score that is basically the product between network weights, theta I, and the gradient that we compute, the absolute value of the gradient. And these brackets here show the inner product. So how does this work? As I said, weights with the lowest scores are discarded, and for training, the network is considered only with the remaining weights, so therefore the efficiency is improved. Obviously, in terms of performance, this is a very efficient method, but it's the initial assumption that the effectiveness of this SNP proxy correlates well with the network performance ultimately is the crux and gives you much better or less good results in some cases. At the other end of the spectrum, very recently, we proposed this approach called ZICO, which comes from zero-shot importance coefficients, which is a method proposed to improve NAS efficiency, again, by evaluating the importance of the network parameters without training. So the key ingredients or the key concepts behind this are first a gradient-based metric. So you see gradients here in both cases. And this essentially is an inverse coefficient variation type of approach, because it looks at the ratio of the mean to the standard deviation. You see this ratio here. And the intuition behind it is that the high values for this ZICO coefficient indicate stable and significant gradients. Therefore, these are the important coefficients to be considered. So long story short, the parameters with stable and large gradients are the ones that are crucial for network performance, and they should be considered, while the other ones can be safely discarded. It's clearly a very efficient method. It's actually data agnostic, okay, because it can work with any type of architecture, but obviously at the end of the day, the assumption that the gradient statistics correlate well with the network performance is what makes the difference in practice. There are some theoretical justifications behind this, why this ratio, why this approach works in practice. I'm just going to summarize two of them. The first one is the smaller the gradient standard deviation across different samples, the higher is the generalization capability, and the lower is the training loss. And the second is that the higher the gradient absolute mean value across these samples, the lower is the training loss. So without getting too much into other details, into many other such proxies that have been proposed, you can see a large number of them listed here. I'll try to summarize here the way they correlate with the actual performance. On CIFAR-10 data set for one of the NAS benchmarks, NAS benchmark 201. And as you could see here, the top winners across this wide range of spectrum of proxies are grade sign, which I didn't talk to. This is very similar to SNP, is the ZICO that I mentioned earlier, and it's also somehow surprisingly the number of parameters. So you can say, well, just the number of parameters of a design correlates very well with the network performance, and you can see from these dots that are derived for two correlation coefficients. SPR is the Spearman and KT is the Kendall-Tau correlation coefficient. The cases which are all, meaning the orange and the green, consider all the architectures in this space. The ones that are with triangles and red triangles and blue circles are only for the top 5 most performant architectures. And regardless of this, you see that these winners clearly separate themselves from the rest of them. So this is an interesting observation when we consider the wide variety of proxies proposed so far. A side note here, although everything I show here is based on classifications on CIFAR benchmark, actually they can be used for generative AI. So for instance, the architectures in general determine the model quality, the diversity, and the realism of this generated data. And efficient architectures will reduce the training time and the computational cost, so will be always in high demand. So I can imagine the use of this kind of zero-shot proxies for quick evaluations and then automate the architecture optimization and get improved performance. Now, there is an important class of so-called gradient-free proxies that have been proposed, and this is one of them that I'm going to mention, which is NN degree. It comes from neural network degree. The main idea is, in this case, is to use network science, particularly the small worldness concept, to decompose a regular DNN architecture, deep neural network architecture, as shown here. This is just a cell, but basically decompose this cell into two components. One is a lattice type of component, G, which is regular and has this level-to-level connections. And one is a kind of random component, R, which has only these long-range links or skip links, which are seen in architectures like MobileNet, V2, or DenseNet, or ResNet type of architecture, some of the most performant ones. And the idea would be to relax the constraints on the width of the network. So basically each cell has a certain width and a certain depth that is proposed, and basically vary these parameters to produce a family of such networks. So formally, this NN degree is defined as follows. So GC is the average degree of a given cell. And as you see here, involves only the width, the skip connections, the number of skip connections, and the depth as parameters. And then it can be shown that the NN degree of a given network, meaning this was at cell level, like this one, but then if you cascade many of them and you get a full architecture, we'd say with NC cells, as shown here, you can simply sum all these parameters and you get a formula that gives you an idea on how this NN degree of a network is. So the intuition behind it, and it can be shown, that the higher NN degree, then the higher the test accuracy. So in other words, if a network has a higher NN degree compared to a network B, you can a priori claim that that is a better architecture even without training. And the beauty of this kind of formula is that it has very few parameters. If you look here, just WC, the width of the cells, the number of skip connections, and the depth, which are kind of architecture type of parameters. So you don't need too many details to figure out this. And therefore, this approach is very efficient. So it can be used, for instance, in fine tuning. To give you a sense of practical application of this, I'm going to summarize here an approach called FLASH, which is based on this NN degree, and it's a zero-shot approach that actually looks at the real hardware constraints. So this methodology has two stages. In red, we show the stage one, which is where basically we build the hardware performance models by randomly sampling candidate networks from the search space and evaluate the hardware characteristics that are of interest to us. So for instance, could be latency, could be energy, could be area, whatever. And then in the blue box, stage two, we actually search for the optimal network architecture, which includes the hardware performance constraints that are estimated, as I mentioned earlier, as well as this NN degree. And by solving a multi-objective function here, F, shown here, which includes all these constraints, we can eventually find the optimal architecture and say this D star is the optimal architecture that satisfies the hardware constraints. Then to verify, we can train this only at the very end to see if what we predicted actually is what we obtained. So from this perspective, the performance that we have obtained on some examples comparing against some of the reinforcement learning-based approaches or some of the gradient-based approaches like DARTS, which is the typical one, the most representative for the single shot, the results are impressive. So for instance, if we look at this data, we can see that we can get a minimal loss in accuracy here in this comparison and a similar model in terms of size, number of parameters, but with the staggering time in less than a second, while the reinforcement learning will need more than 10 GPU hours, and even the single shot will get 4 GPU hours. So in fact, the amazing thing is that this also does not need any GPU to get these calculations. Just a regular CPU is enough. And actually, we got real results on hardware using simple processor and low power processor, and the results were within a few seconds. So it can be very efficient and also account for the hardware constraints that previous approaches that I mentioned in the gradient based category do not satisfy. Finally, one more angle to this from an energy perspective. So in this case, we use an edge GPU hardware device. It's an NVIDIA Jetson TX2 as the target hardware. And we use energy consumption from the NAS benchmark. And then we set different values. So for instance, we set constraints energy to be less than 10 millijoules or less than 20 millijoules. And we compare different proxies as shown in this representation. So some of them are very simple, like number of flops or number of parameters. Some of them are very sophisticated. I didn't even mention in the first category, like the Jacobian covariance, SynthFlow, Z-score, and finally the Zico one. As we can see from this, if we set the energy constraint very tight, meaning say 10 millijoules, we can see that many of them can provide good solutions because the problem is so constrained. But if we relax this a little bit to say 20 millijoules, we can see that the winners stand out in terms of number of flops, number of parameters, and the Zico, which correlates actually the best across the entire spectrum of energy constraints that we may have. So this is an interesting result because it shows that these theoretical things have actually shown good results when implementing directly on hardware, as I said, on this NVIDIA Jetson platform. I would like to give a summary, conclusion of these many existing proxies. You can see here these many gradient-based, most of them I didn't even mention. I only mentioned Zico, and I mentioned only SNP here. In the second category, NNMAS, there are others, and they are fewer, but still there are some of them. And three conclusions can be observed from this. The first one is that the heavyweight lies in the upper half here. So the most solutions proposed to date are in this gradient-based space, which is by nature more sophisticated than the gradient-free approaches. So there is a lot of room to improve in this problem space, particularly if we think about efficiency. The second conclusion is that most of the gradient-free proxies, with a few notable exceptions, are heavy targeting this area. So they try to improve the expressive capacity, while the gradient-based ones try to improve the trainability. This is an issue because, if you remember the initial diagram with three bubbles, I said a good proxy will take care of all three of them. So in general, all the approaches are heavily focused on improving one of them, either trainability or expressiveness here, sometimes like these ones, two of them, but never all three of them. So this shows that there is room for new research in this area to propose more efficient proxies that can make these zero-shot approaches even more efficient. So as a conclusion to this first part of my talk, as of now, we've seen how we can discover good architectures. Good neural architectures that can satisfy real constraints. The problem now is, how do we train them? How can we train them optimally? In other words, to make them make the best use of the available resources. So while in this second part we'll not discover any new architecture, we'll show how can be the original one, the discovered ones, how can they be trained in a very efficient manner. Particularly, this leads me to an interesting class of neural networks, so-called anytime neural networks, which are an interesting proposal in the class of neural networks because they can provide results depending on the availability of the resources. So for instance, if the latency constraint, say, is 100 milliseconds and the classical network like this one will satisfy it, the question is, how can we still do and provide meaningful calculations and provide meaningful results when the latency constraints changes to, say, 50 milliseconds? And we want to provide this kind of runtime flexibility without reloading a new network and starting all over. So again, the same problem. There have been many solutions proposed in this problem space. The problem is that they are ad hoc in nature. So in other words, similar to the first class of approaches for NAS, they are basically kind of trial and error type of approaches. And what we're interested in here, in contrast to this, is to see if there is a systematic way to sort of extend the NAS concept to handle anytime neural networks. In general, anytime computation is an old, very well-established concept. This is just particularized now to neural networks. So the kind of new research that is needed needs to address two questions. So can we quantify the importance of various operations, for instance, convolutions, residual addition, so on and so forth, to the convergence rate and accuracy of anytime neural networks? And second, are there any topological insights, for instance, related to the network structure that can help us design better networks? And the answer to both questions is yes. In the next few slides, I'm going to show you a little bit of how this kind of approach would work. Again, we start with the important abstraction or an important model, which is based on graphs. So we model the input and output and the feature maps as nodes, as shown here. And we model the operations at edges, different types of convolutions, as shown here. And what do we do then? We think of training process as a process that sample some subnetworks, as shown here with 3 different colors here. Depending on the operations involved, you see that these topologies are slightly different. That's why we use 3 different colors here. And the subnetworks that are sampled during the training are actually the networks, the potential networks that will be used for inference. So if you're interested in improving the efficiency, for instance, when you have a real-time constraint, this kind of analysis could be quite useful. So what's the big idea behind it is to model these anytime neural networks as discrete time Markov chains. And you see for each network here, for each subnetwork here, we can associate an adjacency matrix that describes the connectivity between different points. So each node here is one entry in this adjacency matrix. And depending on the links that we have or we don't have, we have ones and zeros as shown here at different points in the sampling process, initially at iteration K, at iteration T. And the question is, once we have these matrices, these small matrices that we deal with, can we connect them to form this kind of, to model this kind of discrete time Markov chain? And the answer is yes. We can add edges among different subnetworks, and we can build this hyper adjacency matrix as shown here. So each entry here is in fact a matrix with different colors showing where it comes from which part of the network. And then on this, we can figure out the stationary probability of this Markov chain, so pi, that gives the probabilities of each node, of each R in this representation, so R1 or RK or RT. And the great thing about it is that once we have these individual probabilities, we can create so-called the topological accumulated score. In other words, we can combine these probabilities to assign a value for each and every node. And then based on this, we can analyze different paths, because this is what matters the most during the training process. Let me explain this. So from node R to node D, we can have in this simple example 2 paths. We can have the path 1, which is RV1D, and therefore RV1D will be 0.3 plus 0.15 plus 0.3 will have a cost of 0.75. Or we can have path 2, which will involve RV2 or D. So just a different type of processing. And in this case, the topological path score will be 0.85 because will involve slightly different probabilities. What the intuition is at this point is that this end-to-end path should emphasize the highest TPS values, the topological path scores, because this is the path that is based on the most important operations as shown here with red. So most important means most impactful operation in terms of overall accuracy in the end. So again, while in the first half, we're talking about the importance of the parameters that ZICO and SNP and all other things produced. In this case, we're focusing on the operations and we're identifying the important operations that can be valued more than others during the training. And to give you a sense of what's the difference between important and unimportant operations, I have these two representations here where we show the top one accuracy for efficient net P0, the cell that I described earlier, and ResNet 18, another class of important networks. And we can see that as we prune these important versus non-important operations, the unimportant operations basically don't matter or matter very little, while the critical ones are the important operations. So this one, the important operations are much more sensitive to pruning. So during the process, the training process, we can emphasize them, we can make sure we preserve them, and we eliminate the others in a similar manner in which we did for the parameters, and the results are impressive in the sense that, for instance, on MobileNet v2, on the ImageNet 1K data set, which is one of the most representative ones for image classification, we can see that the improvement is over 1% in terms of top one test accuracy. And not shown here, but also very important, is that the convergence to the solution is much faster compared to the other approaches, state-of-the-art approaches. These are approaches based on joint width and weight optimization. So these are a particular class of anytime neural networks called slimmable neural networks. So these better results can be obtained just by focusing on these important operations. Again, a side note here, this could be important for fine-tuning because with these LoRa things and all these applications that variations that have been built around it, we can use this technique to randomly prune the network and compute different proxies, zero-shot proxies, then use these values to estimate, the important parameters and the important operations, and only focus on this. So assuming that this gave you a sense of the power of the abstraction or the models that can be used in the neural architecture search as well as the training process, I'm going to illustrate now in a few minutes just two interesting applications that we're focusing on where this kind of very efficient architectures have a place and could have a significant contribution. And I'm going to start with the first one, which is the real-time depth estimation. So long story short, in this case, we're interested in determining at pixel level the relationship, the spatial relationship between objects in a figure. Okay, this could be, for instance, if we look at this image, kind of temperature diagram, which shows which objects are closer to the camera and which one are further. And this can be used, for instance, to render a 3D profile of an unknown space, or could be used in autonomous driving to appreciate the distance to an obstacle, things of that nature. The problem is, for instance, if we use a pre-trained model, the results could be good, say, but when we deploy this, say, on a mobile robot, like shown here, because of the variations that appear at runtime, this could be a serious problem. Not only we can get poor quality, but the results can be slower. And in real-time applications where the like autonomous driving, where the time is a critical parameter, this can lead to accidents or even catastrophic loss of life. So this is an important problem. What I'm going to show here is the direction in which we're working on, which is called online training and inference, or OTI for short, via federated learning. So just assume that we have multiple autonomous robots that can explore an unknown space, say a room, and each of them see a different part of the same room, and then they communicate via the cloud or via a server, an edge server, for instance, a laptop, to update their local models. So all these cameras see different parts of the room, they train locally, and then they share the model with the server, and then the model is aggregated and a better model is distributed again over these cameras at the next iteration step. So what we have in this overall methodology, we have one thread that we use for inference and one thread that we use for training. And basically both threads use a shared buffer, okay, to temporarily store images that are used for training when the buffer is full. And basically this allows us to do at the same time training and inference, therefore improve the quality of the model as we go. So in our simple representation here, we used multiple Jetson Orin Nano devices that run the same inference and training threads locally and synchronize with the cloud to in this case was a laptop, to improve the model. So the aggregated model is a better global model that can be further refined on each client by successive training. Just to give a quick overview of the federated learning process. Federated learning is widely used for distributed learning as an approach where individual clients train data locally, so the data never leaves the local device, which could be, for instance, a cell phone, and then aggregates typically in the cloud or at edge server level these individual models from a certain region to create an aggregated model that is better and is distributed at the next iteration to improve the quality of the predictions. So I have a small, tiny illustration of this, so of our setup. So we have 4 Jetson Orin Nano devices connected to a router. The router is shown here. These are the Orin devices. And we have 2 cameras, which are Microsoft Azure Kinect cameras, to be more precise. You'll see them in a second here. Okay, this one. And the cameras provide images and the ground truth for the depth, while the devices perform in real time both inference and training on the images from the sensor. For instance, so this is the predicted image, and this is above was the ground truth. We'll see it in a second on the other one. Yeah, this is you see the ground truth and the prediction. So the points shown in blue are closer to the camera, as you can see in the real image here, and the ones that show yellow or red are further in the back, which can be observed in this image. It's interesting that this project demonstrated the feasibility of this and obviously of this methodology, but more importantly, show the room for improvement if we use very efficient models locally, because the space is typically limited at each camera, and we can do very well with this kind of NAS models. The second application that we're working on, and I find it very exciting, is what we call batteryless AI, or AI with batteryless sensors. In the last few years, a large amount of machine learning tasks rely on data generated by sensors like cameras, microphones, accelerometers, human vitals on wearables, and whatever. These sensors are often tethered to a power supply, either to an outlet or which makes them static, so they cannot be wearable, or they depend on a battery which needs to be exchanged or eventually recharged, therefore limiting the lifespan. In contrast to this, batteryless sensors leverage the energy harvested from various sources of energy. Could be solar, could be thermal, could be kinetic, and so on and so forth. So they are not tethered to any particular point and can be ubiquitous. So the problem is that the energy harvesting is an intermittent process and a highly unpredictable process, and opens up an interesting research space for using machine learning, for instance, to do human activity recognition, which classifies the images a human does. So for instance, if you assume multiple sensors in different parts of the body, you can trace them And depending on the type of network that you use here, you can classify the movements in jumping, laying in bed, sitting, biking, or whatever. The interesting thing from a theoretical perspective is that this introduces here the idea of seeing the batteryless sensors as optimizable data sources in the edge AI system. These sensors transmit data in a sparse and asynchronous fashion due to the sporadic nature of the energy harvesting process. So basically, we have to process unstructured data using some sort of neural networks. In our preliminary results, used a tiny transformer here, but clearly this is wasteful, and we plan to use solutions provided by NAS to optimize this even further. So from a NAS perspective, what are the interesting questions would be to find novel architectures that are suitable for these batteryless scenarios, and what kind of NAS techniques can be eventually adapted to find better energy spending policies. Because I said the sensors here are seen as optimizable sources. So just to give you a sense, this is a model that we simulated to when we try to synergize the energy spending with the deep learning models. You see here two sensors. So one is from the left leg and one is from the right arm. That start at some point and they accumulate energy. This is the data from the accelerometer. And we accumulate this, and when we reach a certain threshold, we send the packet, then again accumulate and send the packet. And the whole game here is to accumulate and to send the packet in such a manner that we never deplete the energy, and at the same time we make most meaningful decisions, such that you starting from neutral position to identify, say, a running activity or laying on the back or biking or whatever. Keep in mind that the problem here is interesting and quite complicated sometimes because some activities, for instance, playing tennis, will move these sensors quite a bit, so will be a lot of energy accumulated, while others, like speaking on the phone, will eventually move the arm, but a lot less other parts of the body. So finding a balance between when to, how long to accumulate and when to send this packet is a interesting problem to solve in machine learning. To conclude my talk, I want to emphasize a few points. I mentioned the efficiency of the zero-shot NAS approaches that leave a lot of room for improvement compared to previous approaches. In particular, the interpretability of these approaches is remarkable because they rely on or improve our theoretical understanding of why certain networks work better than others without doing the full training. They are pretty much effective in many cases. There are variations depending on the constraint scenarios in particular, but as I showed, the current proxies only typically address one, sometimes two dimensions of the problem, which is less than the ideal 3 dimensions, and therefore new classes of proxies are expected to make a difference. There is plenty of room for improvement, and going beyond the image classification to object detection to natural language processing, speech recognition, and other such applications. From a broader perspective, so not specifically related to the details of these slides, I think the problem of efficiency in AI ML is not just about saving time of resources, but is an integral part of enabling scalable and cost-effective AI solutions that can be widely applied to various domains. The efficiency in AI also enhances our ability to deploy real-world applications where constraints like time, resources, or energy are critical. This concludes my talk, and I would like to acknowledge the students in my team, SLD team, and as well as our collaborators at other universities, and our sponsors in recent years. And we have a lot more information on the website, which unfortunately I think I forgot to put it here, is SLD at UTexas. Thank you very much, and looking forward to seeing your questions.
Yeah, great. Okay, thanks a lot, Professor Marculescu. this is a wonderful talk. Okay, I'm sure. Okay, we will have quite a lot of interesting questions right from our audience. So for the audience, okay, if you have any questions, feel free to unmute yourself and you can ask a question directly to Radu.
Sure.
So I can ask a question. So Radu, thanks for the excellent talk. So you mentioned, of course, limited resources. It's a barrier to deploy AI machine learning to the real-world applications. So what are other factors that you think that we should address? For example, like a privacy concern, or things.
Excellent question. In fact, I hesitated a lot when I tailored my talk because I wanted to have two parts addressing, on one hand, efficiency, and on the other hand, trustworthiness and privacy, which is what you mentioned. I decided to go with this. I thought because this is the part that connects a bit closer to the focus of this embedded and cyber physical systems communities. The one on trust, we addressed important problems there, but is more removed from the hardware constraints, for instance, from the energy constraints. And let me elaborate a little bit on this. So one important constraint, people have been, preserving privacy and whatever. One of the fundamental problems, actually we're working on it as we speak, is the machine unlearning problem. So just imagine that all the focus on the community is heavily tilted toward the machine learning, but we decided to work on machine unlearning and to make that efficient. So the problem is as follows. Assume the following kind of scenarios. So we have a bank, a big bank that has thousands and thousands of clients. And suppose they train a lot of their tools based on the clients over, I don't know, last 2-3 years or last 5 years. The problem is when some of the clients disappear, they take their account and move to a different bank, or some of them simply decided to change their investment approach or whatever completely. So the question is, what do you do with those models? Because there is a lot of private information that is embedded already in the training process. And a company like JP Morgan or whatever cannot afford to deal with this in a lightweight way. Or imagine a situation like I think was pointed out in the New York Times with the copyright issue, with paragraphs that were used, was a story in the spring 2024 where they discovered a lot of paragraphs that were copyrighted from they're copyrighted by New York Times and they have been used in different places without proper acknowledgement. Or imagine even more than this, private information. You don't want to show the face of a child when you do some sort of survey of some properties in a certain area to do even more construction or more development. So the question is, the brute force solution is very time consuming and very costly. So basically to get everything and to retrain from scratch. The question is, how can you unlearn, by using the same model and making sure that the way you unlearn it maximizes the distance between, so to speak, real model, the current model and the previous customers, or minimizes the distance for the current model that you use such that you have very accurate predictions. For instance, if you want to analyze some trending spends. So to answer your question in a very concise manner, I would say machine unlearning is a significant concern that can be used in addition to this efficiency when you think from a privacy angle. Despite the regular privacy issues that you see in a lot of research in this problem space, as well as fairness, for instance, and federated learning. But I think machine learning has a lot of potential because it's a new problem, and it's a problem that ties into the efficiency. In other words, you have to do it in an efficient manner in order not to raise the costs or blow the models up and change completely the entire strategy.
Thank you very much.
Yeah, thanks a lot, too. So do you have any other questions from the audience?
Hello, Professor.
Yes,
Yeah.
please go.
I have a question. I think in fact the deployment, except the deployment of those large models to inference, I think the training and the fine tuning also cost a lot of resources.
Yes.
And are there any recommended ways to fine tuning or training the large model on those resource limited devices?
Mm-hmm. Yes, this is a very good question. So the fine tuning as a way to adapt to the reality or of various environments is a significant problem. There are a lot of approaches that have been proposed, and the ones that are most representative are pretty much all rooted in LoRa in different ways or forms. Basically, the idea is what is possible to do is to project the models into a different space and then do some operations very efficiently there, and then to project the model back in the original space, such that you can improve the efficiency of this. But yes, there is a lot of research. I would say the starting with LoRa and the QLoRa and the online LoRa and all these things, all these are directions that emphasize the efficiency of the process. And I believe that NAS itself can also contribute to this problem space. I'm very much aware of a paper that I saved for me to read. I didn't read it yet, but is in the context of the parameter efficiency, which tries to propose, it's a survey, I'm sorry, which proposes toward the very end, is less than a quarter of a page, a section talking about adapting NAS approaches, NAS type of approaches to do this very efficiently in a systematic manner. But yes, there is a lot of room to use this kind of proxies to drive the fine-tuning process in a very efficient manner. Yes, it's a very hot area, by the way, of research. Yeah.
Yeah,
Thanks, Professor, for your answering. And thanks for your great presentation. Thank you.
Thank you.
Okay, so we have two questions from Ahmed. Okay, so Ahmed, okay, maybe you just unmute yourself. You can ask your questions to Professor Marculescu yourself.
Yeah, thank you, first of all, Professor Marculescu, for a fantastic talk. Incredibly enjoyable. I had two questions for you. The first is that this whole kind of domain, because I come from an optimization theory background, this whole domain of resource-constrained ML appears to be sort of in the category of bi-level or multi-level optimization. And so
yes.
I'm wondering, are you aware of any techniques that have kind of tried to use sort of direct, multi-level optimization techniques in this regard? And if so, how do they compare to the techniques that you have proposed? And secondly, for the machine kind of unlearning problem, do we assume that the original example that we wish to forget, you gave the example of like a customer's data in a bank, do we assume that that's available to us or that's not available to us?
Yeah, very good questions, both of them. I'll start with the second one. In the unlearning problem, yes, we assume that there is somebody who, for instance, curates. At least in our existing work, we assume that somebody curates. So, for instance, looks at some images that are collected by, say, some drones or whatever, and says, okay, we want to use these surveys to characterize a certain land and see potential for development or whatever. And some of the images include faces of children, minors, and whatever. We assume that those are tagged, and there is so-called forget set and retain set. So we assume these sets are available. Okay, potentially this can move into self-supervised learning type of approach where those things are discovered as part of an automated process. But currently, this is the formulation with a retained set and a forget set. So the examples in the forget set are given explicitly, and you said you don't want this. Could be porn, could be violence, could be just privacy type of information. As far as the first question, that's deep, really deep. And for a person that is focusing on optimization like yourself, this is a great angle to this problem. For the flash paper that I mentioned, I point out to read the reference of the, I forgot now, it's called SAGO. I forgot where it comes. Each and every letter is something simplicial type of approach that is used for multi-objective optimization. And those approaches, I think, have a lot of potential for this. So our contribution in that, from an optimization point of view, is that we created an hierarchical version compared to the original version that was published in the high-performance computing architecture many years before. So we created a hierarchical version, but in general, there is a lot of potential in this problem space. And I think your question is very well targeting this direction. Yeah.
Thank you so much. Really appreciate that.
Thank you.
Great. Thanks a lot. Do we have any more questions from the audience?
Yes. Hi, Professor Radu. So thanks for your great talk. So in your talk, you mentioned like the generative learning in resource limited device, and also in the just now the discussion, you also mentioned like about the LoRa, to deploy LoRa in such systems. So I'm wondering, how would you think about the main challenge of deploying such a generative foundation model or with the language model in current real world real resource constraint device?
Yeah, well, very good question. So the idea would be if we can develop some sort of proxy that can very quickly and very accurately characterize an architecture that we want to use for model generation. That's the idea. So in other words, to have something that is tailored. It's kind of model generation on demand. I don't know how to call it, but that will be the idea. We have not done anything yet, unfortunately, but this is primarily due to the lack of inspiration so far, but also because of the time. We started very recently, halfway through the summer, to look at this problem, and there is potential for this, but as of now, I'm not aware of concrete approach that has been done that successfully and can claim the use of NAS for generative AI. I think it's, it's kind of, I'm giving you another example. I don't know if this helps or not, but for instance, when you think about NAS, you may per se, the success stories in NAS, you may say, well, there are a lot of models that have been used, for instance, ResNets, which are used a lot, and they did not rely on any, I mean, the only concept that they use is the one that I mentioned, meaning is the concept of long-range links, and which emphasize the small worldness, and therefore they minimize or eliminate the small gradients propagation problem. But the question is, NAS can be a lot more powerful and produce far more interesting examples compared to this ad hoc type of approaches. Unfortunately, the field is slowly evolving, in my view, because it needs a lot of creativity in terms of mathematical approaches that can be used in this problem space. So for instance, if you look at some approaches like, I think I mentioned it here, ZenNAS. It's an approach proposed in 2022, if I remember correctly. It's very powerful and very potent. Why it has not been tried in the generative AI space, I have no idea. But I think the potential is there, and it will be soon available, at least in some forms, in some papers. So it's more aspirational at this point when I'm mentioning this, but certainly I think it will happen, and it will be potentially a significant improvement in the quality of the models generated by this generative AI.
Okay, thank you. Yeah, I totally agree with your point because also, like you said, I think NAS also could be very promising direction
Yeah,
when we to deal with the delay when we want to deploy such a Kubernetes model on device.
exactly. Yeah.
Yeah.
It's a powerful model, but unfortunately, the progress is not as immediate as we want to. Is needs a lot of thinking, a lot of creativity in modeling, in choosing these abstractions, and it's like it needs to move the needle toward creating a science behind the neural architectures rather than just having good solutions that are produced based on experience and designer's intuition. Yeah.
Okay, thank you. Yeah, thank you.
Mhm.